first three of these are actually identical, because there's nothing to distinguish what we call P1, P2, P3. They're all prime numbers drawn from the same set. So we could just call this function s of alpha and n, and we could multiply it by itself 3 times, or just cube it. By doing this, h of n is now a function of just two things: e to the minus I 2 pi n alpha, which is just a complex number that you could compute, and this new function s of alpha and n. But what is this function? Well, let's do an example. Again, say n equals 11. Then s of alpha and 11 equals just a sum of 4 exponentials, each governed by its own prime number. You can think of each of these exponentials as a clock, each with its own prime number that determines how fast the clock spins. So 2 turns the slowest, 3 turns faster, 5 turns faster still, and so on. But remember, this is a sum, so we actually need to add up all the clocks tip to tail. Now watch what happens as we increase alpha. All the clocks wind around at their own rates. What we're interested in is not the behavior of any individual clock, but instead all of them together. Since we've chosen a pretty small value for n, nothing too exciting happens. But watch what happens if we pick a larger value for n, like 99. Now there are 25 prime numbers that are smaller than 99, and hence 25 clocks in our sum. Now, as we increase alpha, all the clocks again wind around at their different rates. It almost looks like a dragon's tail. And for a while, everything seems kind of chaotic, circling around the origin. But then, when alpha hits 1/6, the tail unwinds. And suddenly, almost all the clocks point in a similar direction, and we get a large resultant value. If we increase alpha further, the clocks cancel out again, until we hit the next magic point, 1/3. Here again, many clocks line up, and this curious pattern keeps repeating. For the majority of values of alpha, the clocks cancel each other out. But at a few special points, like a half, the tail unwinds, the clocks interfere constructively, and we get a large resultant value.
If the angle is 360 degrees divided by a whole number, you get some very particular behavior that's very predictable. Those are the angles at which this function, when you sum the primes, they actually go far from zero. And what happens at a random angle, and you just start adding the primes up, it keeps changing which way it's pointing, and the thing just bounces around.
So why is this happening? Well, let's look at when alpha equals a half. Here, what we're doing is multiplying each prime number in the exponent by a half. In other words, dividing each prime number by 2. So let's do this for each of the primes.